Our instruments have pushed through the veil of ancient starlight, reaching nearly 13 billion light-years across space and time. At the boundary of the known cosmos, one solitary beacon emerges, a single star whose light has traveled across almost the entire history of the universe to meet our eyes. This is Earendel, the morning star, a survivor from the universe's youth and the farthest individual star humanity has ever seen. But what if this extraordinary light in the void isn't what we thought it was? What if, rather than a solitary star, Earendel is something even more complex? An entire cluster of stars, packed so tightly together that their combined radiance masquerades as a single, distant sun. This is the mystery now captivating astronomers around the world, challenging our understanding of what lies at the farthest edge of the cosmic frontier. The story of Earendel began in 2022, when NASA's Hubble Space Telescope first spotted it shimmering in the distant Sunrise Arc galaxy. At that time, Earendel was celebrated as the most distant individual star ever detected. Its light emitted just 900 million years after the Big Bang. The discovery was nothing short of miraculous. It wasn't simply Hubble's sharp vision that revealed Earendel, it was a cosmic coincidence, a phenomenon known as gravitational lensing. Gravitational lensing occurs when a massive object, like a galaxy cluster, sits directly between us and a more distant light source. The immense gravity of the intervening cluster bends and magnifies the light passing by, much like a giant natural telescope. In Earendel's case, this quirk of physics amplified its apparent brightness more than 4,000 times, allowing telescopes on Earth to glimpse a star, or so it seemed, from an epoch when the universe was still in its cosmic dawn. As astronomers celebrated the find, questions quickly arose. Was Earendel truly a lone star blazing in the primordial darkness, or could it be a tightly packed group of stars, their collective glow tricking even our most advanced instruments? To answer this, researchers turned to the James Webb Space Telescope, our most powerful window yet into the distant universe. Using the JWST's sophisticated spectroscopic instruments, an international team led by Massimo Pasquale set out to analyze Earendel's light in exquisite detail. By breaking down its spectrum, the unique fingerprint of wavelengths emitted and absorbed, they sought clues that would distinguish a solitary star from a star cluster. What they found was both tantalizing and confounding. The spectral signature of Earendel, as captured by Webb, bore striking similarities to those of globular clusters, ancient, densely packed spheres of stars that orbit galaxies like cosmic beehives. These clusters can contain tens of thousands, even millions of stars bound together by gravity. In the case of Earendel, the data suggested that what we thought was one star might in fact be many, clustered so tightly that they appear as a single point of light, even to our most powerful telescopes. Yet the mystery is far from solved. Brian Welch, the astronomer who led Hubble's original discovery, points out that the Webb data alone cannot definitively settle the debate. At such extreme distances, the light from a lone massive star and a crowd of smaller stars can look almost identical. The cosmic lens that magnified Earendel's light also blurs the sharpness we need to be certain. To truly distinguish between these possibilities, astronomers hope to catch a rare phenomenon called microlensing, a brief, telltale flicker in brightness caused when a smaller object passes in front of the cluster, momentarily changing how its light bends and reaches us. The stakes of this cosmic investigation are immense. If Earendel is a single star, it would be the most remote individual star ever observed, offering an unprecedented glimpse into the lives of the universe's first generation of suns. If it's a star cluster, it would still be a record-breaking discovery, revealing the earliest building blocks of galactic assembly just a few hundred million years after the Big Bang. Either way, the quest to uncover Earendel's true nature is a testament to the ingenuity and ambition of modern astronomy. With Hubble and Webb working in tandem, scientists are pushing the boundaries of what's possible peering deeper, resolving finer details, and rewriting our cosmic history with every new observation. The universe, it seems, always has another secret to reveal, just beyond the reach of our current knowledge. As astronomers continue to debate and investigate, Earendel stands as a symbol of both the triumphs and the mysteries of space exploration. Its light, magnified by the universe itself, connects us directly to the earliest chapters of cosmic evolution, a luminous thread woven through time, drawing us ever onward in our search for understanding. Yet, as with so many discoveries at the frontier of cosmic exploration, new evidence has stirred debate and intrigue. Astronomers now question whether Earendel is truly a solitary star, or something even more remarkable, a tightly bound star cluster shining as a single brilliant point from the dawn of the universe. Fresh observations from the James Webb Space Telescope, or JWST, have pushed the limits of our understanding. Using its powerful infrared instruments and highly sensitive spectrographs, researchers led by Massimo Pasquale analyzed the precise light signature of Earendel. What they found was both exciting and perplexing. The data suggested that the characteristics of Earendel's light closely resemble those of known globular clusters, ancient, spherical gatherings of stars found in the halos of galaxies. These clusters can contain hundreds of thousands, even millions, of stars packed into a relatively small region of space. This possibility is as fascinating as it is challenging. If Earendel is indeed a star cluster, it would mean we are glimpsing not just an individual beacon, but a multitude of ancient stars, all bundled together in the earliest epoch of galactic formation. The implications ripple across our theories about the early universe, the formation of stellar populations, and the assembly of galaxies. However, the story is far from settled. Brian Welch, the astronomer who led the original Hubble discovery, emphasizes that JWST's data, while suggestive, is not definitive. At such immense distances, nearly 13 billion light-years, the light from a single massive star and the blended glow of a tight star cluster can look nearly identical. Even with JWST's unmatched resolution, distinguishing between these scenarios is a formidable challenge. The subtle differences between the light curves and spectral fingerprints become difficult to tease apart across such a vast gulf of space and time. One tantalizing method to resolve this cosmic mystery lies in the phenomenon of microlensing. As stars, planets, or even dark matter objects drift between us and Earendel, their gravity can act like tiny magnifying glasses, briefly amplifying the light from the distant source. If Earendel is a single star, we might expect to see sharp, dramatic spikes in brightness as these microlensing events occur. If it's a cluster, the pattern would be more subdued and complex, with overlapping signals from many stars. Detecting and analyzing these fleeting events could provide the crucial evidence needed to unravel Earendel's true nature. Regardless of whether Earendel is a lone star or a stellar ensemble, its discovery has already redefined the limits of our cosmic vision. The gravitational lensing effect that made Earendel visible is itself a marvel of physics. The immense mass of a foreground galaxy cluster warped space-time, bending and magnifying the light from the Sunrise Arc galaxy, where Earendel resides, by a factor of over 4,000. This cosmic lens transformed an otherwise invisible object into a detectable point of light, allowing us to peer further back in time than ever before. Through the combined power of the Hubble and James Webb telescopes, astronomers have turned the universe itself into a natural observatory, harnessing its own gravitational architecture to expand our view. The images and data streaming back from JWST are already rewriting textbooks and challenging long-held assumptions about the early universe. In the case of Earendel, the telescope's spectroscopic data allows scientists to dissect the composition, temperature, and movement of its light across the spectrum, searching for the telltale signatures of its origin. The question of Earendel's identity touches on deeper questions of cosmic evolution. If it is a cluster, what does that tell us about star formation in the first billion years after the Big Bang? Were the earliest generations of stars more likely to form in clusters, or did solitary giants like Earendel blaze alone in the primordial night? The answer could illuminate how galaxies first assembled and how the chemical elements necessary for life were forged and distributed across the cosmos. As research continues, astronomers will be watching closely for additional microlensing events, subtle shifts in the spectrum, and perhaps even new surprises as JWST continues its survey of the distant universe. Each observation adds another piece to the puzzle, guiding our understanding of how the cosmos transformed from a glowing cloud of hydrogen and helium into the tapestry of galaxies, stars, and planets we see today. The investigation into Earendel's true nature is more than a quest to label a distant point of light. It is a testament to humanity's relentless curiosity, our ability to harness technology and nature itself in our pursuit of knowledge. With every new dataset, we inch closer to answering fundamental questions about our origins and to discovering what other wonders await us in the depths of space. As the universe continues to reveal its secrets, astronomers and engineers are refining their techniques, pushing the boundaries of what is possible. The interplay between gravitational lensing, advanced space telescopes, and the subtle analysis of light echoes the intricate dance of the cosmos itself, complex, dynamic, and endlessly surprising. The saga of Earendel is a vivid illustration of how each new discovery, no matter how small or distant, can transform our understanding of the universe as a whole. And so, the search continues, not just for Earendel's identity, but for the countless other mysteries woven into the fabric of space-time, mysteries that beckon us ever onward toward the edge of the observable universe and beyond. The story of Earendel, once hailed as the most distant star ever detected, has now taken a dramatic turn, and with it, our understanding of the early universe continues to evolve. When Hubble first caught a glimpse of that tiny ancient pinprick of light, astronomers were awestruck. Here was a single star, or so it seemed, shining across nearly 13 billion years of cosmic history, its light bent and magnified by a powerful gravitational lens. It was as if the universe itself had handed us a window into the time when the very first stars were formed. But as is so often the case in astronomy, closer inspection brings more questions than answers. With the unprecedented power of the James Webb Space Telescope, researchers like Massimo Pascali and his team were able to dissect Earendel's light with exquisite precision. What they found upended expectations. The light signature looked less like a single, massive star and more like a tightly packed cluster of stars, perhaps the core of an ancient globular cluster, or even a small galaxy in the making. This revelation doesn't lessen the wonder of the discovery. In fact, it opens up even more tantalizing possibilities. If Earendel is a star cluster, it may represent a snapshot of the kinds of stellar nurseries that populated the cosmos less than 1 billion years after the Big Bang. These ancient clusters are thought to be the building blocks of modern galaxies, their stars forged from the primordial elements left over from the universe's fiery birth. The debate isn't settled, however. The faint, distant light that reaches us from Earendel's corner of the Sunrise Arc galaxy is incredibly challenging to interpret. Because clusters and single massive stars can produce remarkably similar spectral fingerprints at these distances, even Webb's advanced instruments can't provide absolute certainty. Some astronomers suggest that the cluster hypothesis is the most plausible, but others, like Brian Welch from the Hubble team, remain cautious. They point out that only future observations, perhaps of fleeting microlensing events or more detailed spectroscopy, may finally reveal the true nature of this record-breaking object. What's clear is that discoveries like Earendel push the boundaries of what is possible, both technologically and intellectually. Gravitational lensing, that cosmic magnifying glass, has emerged as one of our most powerful tools for probing the distant universe. It allows astronomers to study objects far fainter and farther away than even our largest telescopes could otherwise resolve. In the case of Earendel, the lensing effect magnified its light by a staggering factor of 4,000, turning a faint whisper from the dawn of time into a signal we could study and debate. As we look ahead, astronomers are already planning new campaigns to monitor Earendel and similar candidates. They hope to catch subtle fluctuations in brightness, microlensing events that could distinguish a single star from a cluster of stars. And with each new round of data, our models of the early universe grow more sophisticated, teasing out the details of how the first galaxies assembled and how starlight reionized the cosmos, transforming it from a cold, dark expanse into the vibrant universe we see today. It's a reminder that the universe is not static. Our interpretations shift as new instruments come online and new data challenge old assumptions. The discovery of Earendel, whether star or star cluster, illustrates the dynamic nature of science, constantly revising, refining, and reaching for deeper truths. And as astronomers peer even further into the depths of space with next-generation observatories, more surprises are inevitable. Each discovery, each flicker of ancient light, brings us closer to understanding not only where we come from, but how the cosmos itself has changed over billions of years. Earendel's saga is far from over. With every new observation, we peel back another layer of cosmic history, learning not just about a single point of light, but about the vast, interconnected web of stars and galaxies that make up our universe. If you found this journey through the mysteries of the cosmos as fascinating as we did, make sure to like this video and subscribe for more content like this. There's a universe of wonder waiting to be explored, and together, we'll continue reaching for the stars. For the stars.